Okay, well, it's 10 o'clock, so we'll make a start, and hopefully people will keep on joining us as we go along. So first thing I'd like to do, of course, is to welcome you to our EU Green Week webinar hosted by our EnlightEVs Cluster, which is a cluster of projects funded by the H2020 research program. And they are all focused on one thing, even though they do several different things within that field, and that is, of course, to try to make our electric vehicles of the future to be lighter, more efficient, and more practical. By enlightening them, we make sure that the battery can last longer, so we have an actual battery electric vehicle instead of a battery on wheels. And of course, we also try to make sure that we have a lot of thought for whether these new concepts and ways of making things lighter are also sustainable. So I always say we don't just a lot of things that obviously seem to be sustainable and better for the environment, but we don't know until we really do the research and find out what it is that is possible or not. We are very grateful for the EU in this case to acknowledge us as one of the official side events for the Green Week, whose theme this year is, of course, green skills. I think that this is a particularly important topic at the moment. There was a report from LinkedIn at the beginning of last year that noticed that there was a discrepancy in the growth of green skills demand and the growth of green skills supply. So I think that the EU is also busy with this topic, trying to make sure that we have the skills and the know-how, the knowledge within the industry to make the changes that we think are important. This is also why most of our projects here today have been thinking about not just what it is that we have to do in the future, but also how do we make it possible for us to integrate that knowledge and those new technologies and concepts into the industry and make sure that they get actually used. So we have the great pleasure today to be also joined by Mr. Maurizio Maggiore. He is a senior expert with the DG Research at the European Commission, and he has very graciously agreed to tell us a little bit about how he sees the lightweighting component of the research that we're doing in context, of course, of the EU research in general. So, Maurizio, can I please ask you to say a few words to welcome everybody and introduce the topic?
Thank you very much for inviting me to this webinar, and welcome to all the participants which are online. Let's say I've been concerned with this topic for a long time. This has been a subject of a long series of projects. I still remember writing the topic that led to Superlight Car, which was the first large project which delivered a complete vehicle structure and not just a few components like happened in previous projects. This was framework 6. And then we had in following frameworks, Live and Light Alliance, and the projects which are in today's event. However, I still have problems seeing the implementation of all this series of projects. And I think this is an important objective for all of you who are involved. Many of you have been in these previous projects to really dig where those technologies were implemented, because we have more and more pressure about this, and in this particular area, it's difficult to justify that this is specific for electric vehicles. Lightning is indeed improved, needed to improve sustainability, but that's not achieved by reducing 10% of the weight of a hammer. So industry, I think, should look beyond making using lighter materials or lighter structure, but really also looking at lighter concepts. So it's a combination of the two that works. Otherwise, it will be difficult. But in any case, as I say, it's important to show where the technology has been justified in the future to keep these type of projects for lightweighting, and then I will explain why I'm underlining this in the future. For EVs, indeed, it's less and less clear what the real benefit of only working on the lightweighting of the structure. I remember that the ALMA proposal in the text explained that at the time, and we are talking about a time when batteries were very costly, the lightweighting didn't pay off compared to the saving in the battery size. So, and this, as I say, has been a long time. So making this kind of calculations again to understand what is feasible and worth doing, it's, I think, an important task that you as a group are very well placed to do. And the reality, in my view, is that all types of vehicle benefit, and in reality, is internal combustion engines, propelled ones, that have the biggest benefit. So it's there that we should see these technologies implemented. And as I say, I cannot see, because I have no feedback on the implementation of the projects. For EVs, the fact that the batteries are becoming denser and denser, I think makes this question even more important. And even there, I'm not seeing electric vehicles, at least in Europe, because we know that Tesla is doing a great job by totally changing the technology. But here in Europe, I don't see this application and these vehicles becoming lighter. So I think let's say, those of you who are in industry should really be outspoken and clarify these things to us in the future. As an example of why I'm particularly concerned, I remember an old project, something like 20 years ago, the Apolis project, which did basically the main structure of a sports car completely in carbon fiber. And already at the time, we were looking at LCAs. And the result was that the cost of the fiber in terms of CO2 barely paid back in the life of the vehicle. And that was an internal combustion engine vehicle. So I know that carbon fibers have improved, but I think it's important in this case and in all cases to really see, as you said at the beginning introduction, the global benefit in terms of life cycle assessment. Because, as I say, on one end, it looks like it's less important than internal combustion engines. And on the other, if this means using sophisticated materials, I think we need hard evidence of the benefits that it can provide, if at all. Otherwise, it's interesting to look at other type of structure like Tesla is doing. And of course, as I mentioned, carbon fiber, which is probably one of the worst examples in terms of intensity of carbon. But what about aluminum as well? Because I said Tesla is doing this job, but they're using basically big chunks of aluminum. So I have questions, and I would like to have answers from the experts that are in this workshop. So this is just to say that we might be transitioning, and we actually doing it, from lightweighting to LCA-driven projects. So lightweighting per se might not be the holy grail. We have to look at the LCA effects of the materials and find which is the best compromise for the future. And as I say, we are doing it. So we have the recently started LCA project in which a lot of the people around the table are involved, because of course they have to feed the data, the real data. We want only real data, no more databases or something like that. We want to know that car, how is the LCA of that car, and compare it with the other car manufactured in China with real data and not just. And at the same time, we will have this circular car, which is the other, let's say, frontier of vehicle structures. So LCA, but also recycling and using recycling materials and designing for facilitating the recycling and reuse of the components. So I think the expertise which is present is what we need for answering these questions. Sorry for asking so many, but I think we need to have, let's say, hard-nosed approach to these things, because, as I say, we get challenged by the Parliament, by the Council, on what to do in the future, how much money to put into the research projects. And I think that these are legitimate questions, and we need to provide answers to all the stakeholders, and at the same time make vehicles which are closer and closer to real sustainability. You say that we don't know. I think we have some doubts here and there, some I raised, and we really need to find out whether it's better, which I think personally is true, a heavier EV than a heavy internal combustion engine by several times. So the mix, let's say, of concerns is slightly changing, and therefore this the choices done in this project and then in the design of vehicles needs to go into this direction, which is the global sustainability and just not one aspect of it. Thank you, and I'm eager to see the development of all the presentation. Thank you.
Thank you very much, Maurizio, for that great introduction. I'm sure that you will get all of your questions answered by the end of this webinar. We certainly have all the experts also working on aluminium and composites who have been looking very much, as you say, into that LCA approach as well to their different designs. So I would like to make a start to the webinar proper. We have a packed agenda today, so we will not spend too much time and more in the introduction. Today, we have 5 projects, as I mentioned to you earlier, all part of the EnlightEVs cluster. We have the ALMA project, which we'll be presenting first, followed by Fatigue for Light, Flamingo, Revolution, and Levies. To start off with, I would like to introduce you to the ALMA project, who will be presented by Ms. Vanessa Ventosinos from CTAG, who will also be joined by Pascal Lorenzini from ArcelorMittal to talk about materials, and Tom Lichthart, who will then also highlight on how we've done LCA to make sure that all of our designs are actually improving sustainability. So, without further ado, I would like to introduce to you Ms. Vanessa Ventosinos.
Thank you, Jose. I'm going to share my screen. Let me know if it works properly. Okay, can you see my screen?
Yes.
Great. So thank you very much for this opportunity to present ALMA project. The main goal of ALMA, in fact, is rethinking the electric vehicle structure in terms of sustainability. So to do so, we have adopted like 2 strategies. The first of all is lightweighting. It's certainly related with the energy consumption of the whole vehicle, but we have approached this lightweighting from an eco-design perspective. So we have introduced to the design not only this lightweighting potential, but also all the life cycle assessment, as previously mentioned in the introduction, in fact. And the second strategy that we have following is to promote the reuse and recycling at the end of life by promoting the sorting of all the parts, using the bondable adhesives and the bondable unions that promote this sorting at the end of life, and the monitoring of the state of each part at the end of life. So in the consortium, well, CITAC is the coordinator, but we have also TNO who developed the LCA and LCC tool, BEVSIM, that is going to be explained later, Fraunhofer for modeling, for validation, ArcelorMittal and BATS for new materials and innovative materials. Pascal from Arcelor is going to explain a bit about that. So we have chosen as advanced materials steels, and SMC based on glass fiber reinforcement, not only because of their performances, but also because the cost effectiveness of such solutions, because it's easiest to bring this innovation into the market, into the mass market, if you are considering also the costs. So today, in my presentation, I'm going to be focused on the design, the eco-design approach that we have followed. So our motto was to choose the best material in the best location and to take profit of these new materials in terms of geometries and functionalities, changing the whole design of the structure. Okay. So in a lot of applications and a lot of systems and subsystems, steel was the only option because of the very high and demanding crash performances in different systems. But in other ones, there was a doubt about which option can be the most suitable in terms of what to choose: SMC composites, steels. And this system were the dash panel, the rear floor panel, the battery lid, and the rear tray. So to choose the best option, we have followed an assessment, an eco-design assessment that weighs different parameters. The first parameter was to assess the weight saving potential of using each material for each of these subsystems. The other parameter was the circularity. So if the components can be recyclable or not, or easily disassembled at the end of life or not. So we have also weighted this parameter. We have included also as a key factor the number of references saved, because we have changed the design. So in using these very advanced materials, we were able to implement different functions in the same part, which is not only suitable for sustainability point of view, but also for costs. And as I mentioned, our goal is to bring all this innovation into the mass market. So it's a key factor. And talking about that, another key factor to bring the innovations into the market is the compatibility with the current assembly lines in the OEMs, so that these new concepts, these new materials cannot change radically the assembly line that we have today, in order to be sure that these innovations can be adopted as soon as possible. So this was an assessment in a sense a bit qualitative, but we have also combined this assessment with LCA assessment, which was more quantitative. And to do so, we have used a tool that was specifically developed for ALMA project. Our colleague from TNO, Tom, is going to explain it a bit. So we have combined both approach in order to choose the best material for each of these subsystems. And we have come to this conclusion that the structural SMC was the best option for the battery cover and the dash panel. And we choose different grades of advanced steels for other parts that allow us to rethink, for example, the H-frame and the door panels to have a lighter and more performance structures. After this redesigning, of course, we follow an approach to validate that this new concept works in terms of crash. To do so, we have followed a Kai crash validation, so it's a simulation with 5 different scenarios of crash, and we reach a fully validated design, which reach at 23% of lightweighting compared to the baseline. We are quite happy with this result because our initial goal was 20%, so we have reached our goal in fact. So this is just our first introduction in ALMA in terms of eco-design, and now I think that our colleague Pascal from Arcelor is going to explain a bit about the advanced steels and materials. Pascal, I don't know.
Yeah, okay.
Yeah.
Thanks, Vanessa, for giving me the floor. So I'm going to share my presentation. So just confirm me you see it well?
It looks good.
Okay. Okay, so just some words about our company at ArcelorMittal. We are the leading steel supplier for automotive, as we provide around 70% of the global worldwide automotive market with the widest product portfolio, and we rely on a global network of R&D labs, both in several European countries, North America, Brazil, and so on. And in our strategy, we are strongly involved in relationships with car makers on co-design activities. So what about our involvement in ALMA project? We support the car maker Ford and CTAG in the implementation of new steels in the car design. So up to the production of demonstrators on the solutions. And Vanessa told some words on quite, let's say, already well-known solutions, steel solutions for those who are involved in car lightweighting, such as the door rings made of new steel rails, or the H-frame made of press-hardened steels. And specifically in the field of ALMA project, we developed new steels with advanced properties to optimize the lightweighting, which was shown by Vanessa previously. So I'm going to highlight now these kind of steels, which are sorted in 3 categories, depending on the kind of parts on which they can bring lightning. Firstly, a very high string steel grade called 44 S1270. So 1270, why? Because it's the minimum value of its tensile strength. And so it's dedicated to the lightening of structural parts. So, shortly speaking, it's a medium manganese trip steel with a quench and partition microstructure. And regarding its in-use properties, we validated its formability, which is close to that of dual phase 780, though the mechanical properties are far more high. And of course, it leads to optimal crash performance. This is the main goal for structural parts, together with an ability to be spot welded following conventional process. So that's one I want to figure out by saying without any post welding head treatment, which would make the process longer, and so it's not what we want to do, of course. It exhibits a good resistance to let's say, what is called ALMAs. So this is a very important problem that on some grades OEMs are facing. And it has a good resistance to delayed fracture also due to its low erosion and brittlement. So here, just as a matter of illustration, you see what are the foreseen applications. So in the frame of ALMA project, we obtained a weight reduction on this kind of parts around 30%. And these parts are mainly reinforcements, crash boxes, roof cross members, as you can see on this picture. So let's now come to a second kind of steel, which is a laminate. With a core layer of thermoplastic polyamide. And this is sandwiched between two very thin steel sheets, which are interstitial free steels for durability. The fact is that due to this specific structure, we can reach a very interesting wave saving around 40% at iso stiffness, bending stiffness, and with a good formability of the laminate. These thermoplastics are compatible with the e-coat process and are also self-adherent to the steel. So this is very interesting in terms of processability. So contrary to the 1270 grade, the objective is to target non-visible panels, but without structural functions this time. So like floor panels, hood inner or trunk inner. You have, for instance, an illustration of how a hood inner can be formed without any crack using this steel laminate. And in the frame of the ALMA project, we developed press technology aiming at delivering large samples in view of demonstrators. And so the third example of steel, which was took on board in the frame of ALMA project, is a low density steel. The objective of which is to lighten the outer panel this time. So you see that the goals of each our steel grades are complementary. And what's the technical value of this solution? Thanks to the addition of around 6% of aluminium in the metallurgy, we reach a density reduction to 7.2 instead of 7.8. And this kind of steel has an excellent dent resistance, which is a key properties for outer panel, with the same yield strength as Dualfast 600. And this kind of concept enables to adapt the range of ductility achievable through the adaptation of the ratio of ferrite versus austenite in the microstructure, because this is a duplex microstructure. That's why it's called a duplex concept. And main results of our involvement in the project is, on the first hand, the adjustment of the target to the spec of the outer panels in terms of uniform elongation to be reached. The adaptation of the hot dip coatability process to the high aluminum and manganese contents of this kind of steel, And so the verification of formability, which is compatible with the specification of today thinnest outer panels made in the best of class steel grade for this kind of uses, which is dual phase 500. And again, as previously on the steel laminate slide, you can see the kind of panels which are targeted, so doors and hood outers, trunk outers, and the saving potential which was calculated in the frame of ALMA project. So that's all for my presentation. Thanks for attending to it.
Thank you, Pascal. Now we have Tom Lichthart from TNO.
Yeah,
Talk about LCA.
I'll take over and try to keep it short. Let's see, and now I have to go to the, sorry, lost the mouse. Yeah, I think you're able to see it now.
Yes.
Yeah, so the BEVSIM tool made by a team of colleagues give a very short presentation on that. So it's an LCC LCA tool designed for non-LCA experts and with the ability to compare design alternatives. And as you see, it has been applied in BEVSIM, and it gives, well, fast LCA results. Then it's, yeah, well, of course, with a LCA part and LCC, but also a circularity indicator in it, and including the full life cycle from the materials, processes, use phase, also the end of life, and you can apply different scenarios for especially for the end of life, but also for the electric vehicle, select different electricity scenarios. You can edit a full car in BEVSIM, but also do it on the level of subsystems or even parts. And with that, you have a large freedom to make your own comparisons. You select a user design and can compare that to two different references. And so immediately see what your design choices have an effect. We, as said, full life cycle, so material, the processes, assembly processes, and very important, of course, the use phase. In green, you see the internal combustion engine, and in blue, the battery electric vehicle. And it's clear that especially the battery, you have a larger impact of the battery, of the materials, but it is paid out in the use phase. There you see that the internal combustion engine, a petrol car in this instance, has a much higher impact, and overall that gives the battery electric vehicle a better performance. You can also do the, here you see the global warming potential, but also other impact categories from recipe can be shown, and the life cycle costing results can be shown. I will not show it. And we have the material circularity indicator. So that's an indication on how your circularity of your design is working. The closing remarks, it's on the full life cycle that you can do the studies. And because it's much simpler, but still offers a full LCA, you have significant savings in time and efforts. And still you can put LCA in directly into your design process. The BEVSIM tool also has the advantage that it's consistent, and you can have access if you send me an email. There is a small fee based on it, but please, contact me if you want to have a demonstration or access. So I hope I gained some time with this presentation. And as said, thanks for your attention, and feel free to contact me to know more about the BEVSIM tool. Okay.
Mute. Sorry, I was on mute. Thank you very much, Tom, for that presentation. Unfortunately, we had a little bit of a technical glitch and we couldn't see your presentation slides, but we will share the presentation slides with everybody along with all of the presentations from today. And of course, the recorded video so that you can always look at that later and make sure that you didn't miss any part of that. So moving on, it is now my pleasure to introduce to you the next part of our webinar, which is from Fatigue for Light. The next contributor will be Maria Violeta Parra from EURECAT. And she will be talking to you, of course, about circular economy, eco-design, and life cycle assessment approaches to enhance sustainability of mobility solutions. So, Violeta, the floor is yours.
Thank you, Jose. Yeah, well, I was planning more on introducing to you to the eco-design methodology that we developed within EURECAT, and we've been applying to this project and other projects that we're working on as well. So, but first of all, we need a little bit of introduction to this and why we're doing what we're doing. So in Fatigue for Light, we have some goals. We are aiming for a 24% reduction on weight. We're also aiming at weight savings from structural vehicle weight as well. We are developing material solutions with high fatigue performance, such as the ones that you can see on the screen, probably. We are developing new computer modeling techniques for more accuracy in fatigue prediction. And finally, and most importantly for me, the affordability of these techniques and the developed materials, which is also including the part of sustainability, applying life cycle assessment, life cycle costing, and of course, eco-design. But how do we do this and why do we do this? Well, we all know how are things right now and how we've been accelerating in population growth and also global warming potential and other climate effects. So that's why we're doing this. And the reason this is happening is because of this formula that someone else we didn't do this. It was Mr. Barry Commoner, along with Paul Ehrlich and Joel Holdren, who developed this formula that where they found out that all the environmental impact is created by the population, the consumption of this population, and the technology that we're using. So we can see where we can improve here. We cannot reduce population. We may reduce consumption, but we can basically, and for most, make our technology better. And how do we do this technology better? By making it greener, by making it more sustainable, more ecological, if you want to call it this way. We want to make this technology, or all our processes, all our products, more eco-designed. So we have eco-design as a concept, as a methodology, and the ISO 14062 defined this eco-design as an activity of design that integrates also environmental impacts into design and development. The main goal is to anticipate and to minimize this negative environmental impacts during the lifetime of any product, process, or system by designing at the beginning of the development of anything that we do. But how do we include this, or how do we integrate this environmental impacts into design? We would have to measure it somehow. So that's how we coupled design with life cycle assessment to make it a real eco design, right? We know that life cycle assessment is a systematic analysis that includes all the life cycle stages of a product, material, or system. And this methodology includes several steps. You can see them on the screen, like defining what we're going to study, the goal and scope, the unit that we're going to use to measure all the flows, the inputs and outputs of the system. Then with this information, we create an inventory, and then we evaluate this inventory in terms of the impact that they're creating in the environment, and we analyze this result. Having all this information, then how do we do this? Well, we developed a methodology that includes both eco-design and LCA methodology within. And we started by saying, well, what's the easiest way to plan this eco-design in a very structured and easy way that can be applied to any kind of product or any kind of study that we want to go through? So we went to the Plan, Do, Study, Act that we all know. We went to the basics. So we have 4 basic steps. First, we identify where we have to focus, because sometimes we focus on the very small things that don't have a really big impact, or sometimes just very small things have the greatest impact. But how to know this? And we do a preliminary LCA on whatever we're going to study, and we find the hotspots in the life cycle stages. We identify where we have to focus. Then there's a second step where we establish the most properly designed for circularity or eco-design strategies based on what we have to focus on this hotspots that we found on step 1. Then on step 3, we align these different strategies that we may come up like brainstorming from our perspective from LCA practitioners. And then we align this to the technological procedures. So we make sure that these strategies can actually be applied. And then on step 4, we select with the help of the consortium, in our case, in Fatigue for Light, we define specific actions that we can go through that can be applied technically, economically, and that they're better for the environment. So this is more or less how we did it for Fatigue for Light. It's only one slide for each of the steps, but it's actually a lot of work behind this. For step 1, we define the hotspots and main issues for the different life cycle stages. In this case, I'm only presenting the raw material extraction, manufacturing, and assembly. That is the first stage that we consider for Fatigue for Light. And we found that we could improve this, that the impact that this stage has within the life cycle of Fatigue for Light was to more or less in between 35 to 50% of the impact. So it's a really big issue, and we should focus on this stage. And then we found a few hotspots I'd like to focus more in deeply, like the electric vehicle production stage could be higher, so we can focus on materials and the processing of these materials. Also, the use of critical raw materials could be a problem. Well, in any case, we can see them and read them on the screen. This is what we found for only this stage. As I was saying, it's very simple. I wanted to keep it short for you. But you can also contact me for more details and further time. Then for step 2, we define a set of strategies and the setup of the strategies. So this is what we found. We found 9 different strategies that we could apply. We made a description. We found like how much impact would have this strategy on each of the different life cycle stages. So we could present this and explain it to the consortium. And after that, we readapt to feasibility with the help of the consortium. We had gathered people from different departments of the companies, design, management, more technical and more management as well, because we wanted to make sure that these strategies were feasible in any possible way, technical, economic, and that were better for the environment. So some of these strategies were actually at the end not considered for the study after seeing that it was not viable or not feasible from an economic or from a technical perspective. After that, having the strategies very well defined and agreed by the consortium, then we went for the definition of specific actions to take place within the project. So I'm not listing the specific actions here because it was very long and it wasn't visual for the presentation. But we used analytical hierarchy process to judge not only the actions, but also the strategies. We did some scoring for these actions and strategies, and we'll find a final score for each of the actions. In this way, we can focus on the highest score that from the point of view of the consortium, that is probably, it has a bias, of course, but is the more objective scoring that we could find so far. And we can focus on the most beneficial actions from the perspective of the whole consortium. So this is what we've been doing in Fatigue for Light, and also in other projects we've been applying. And we found that this is really boosting teamwork with all the consortium with different profiles. And this really improves communication and also boosts the confidence of the people that's working in the decision process. Enhances the implementation of different technologies and procedures when it covers the whole life cycle of the product, addresses directly environmental perspective, and not only directly, but continuously all through the project. And we can find tangible environmental impact reduction after applying all this. I wasn't going to present any results, so that's why I have the conclusions. And then I added just a little slide with preliminary results that I wouldn't like you to take as the final ones because they're very preliminary. So we have this result for a demonstrator for the cross-beam member. We have two different materials, and we can see the effect of the weight reduction in the use stage of, in this case, is a battery electric vehicle, but we did the study for different kinds of vehicles, electric, hybrid, and battery. And I think that's it. So we can see that reducing the weight in a 30% in this case, we can get 23% lower environmental impact for this demonstrator. And that would be it. I hope I didn't do much time.
Thank you very much, Violeta, for that great presentation. We will now move on to our next presentation, which is from Flamingo. So I would like to welcome Mr. Toze Petkov from the Österreichisches Gießerei-Institut, which I have to admit was a difficult thing to pronounce. So I hope you can do a better job of that.
It was great. Thank you for inviting, and good morning, and thank you for joining this event and my presentation. I will share my screen. So, yeah, hopefully everybody can see my presentation. Yeah, I will talk about the Flamingo project itself in the next few slides, and then move on to the topic of health and safety for handling of nanoparticles, and having also a look on the impact of the project. In particular, Flamingo targets the weight reduction of vehicle by improving properties of existing aluminium. This means less material for same or better mechanical properties, and the components can compete with steel. The aim is to improve the properties by introducing nanoparticles into a metal matrix. And in this project, we have a steering knuckle from an electric vehicle, which is made of steel. By using nanoparticles reinforced aluminium and topology optimization, we were able to replace the part with a casted aluminium component with less weight and comparable properties. The project started in February 2021, and we are a little bit above the half of the project, of the duration. And the consortium consists of 11 partners from 8 countries. It's a 4-year project and divided into 10 work packages. Yeah, here you can see the electric vehicle that is produced by Alke in Italy, in Padua. And from a casting perspective, we are focused on the steering knuckle, but also in the project, we are optimizing the rear frame here. And we see what is possible by optimizing the material and reinforcing the aluminium. We can save about, let's say, 68% at the steering knuckle and about 35% at the rear frame. And these results can be also extrapolated for the whole vehicle afterwards. So an overview about Flamingo. These are some of our technology involved in the project. It all starts with the material, with the nanoparticle, and it's not easy to work and handle nanoparticles, so it is necessary to have a safe material, and therefore there is the metal alloying with solid state milling. This is made by a project partner, MBN. They have a high energy milling where they can produce every composition we want, and we tested also different nanoparticles in combination with aluminium and aluminium alloys different. Another technologies we used in the project is the casting part. We cast it in green sand casting and also in low pressure die casting. Did topology optimization from a very simple steel part to a more complex aluminium part with less weight. Also, one part is extrusion. Also, the wettability assessment, also, and non-destructive testing, and also destructive testing of the components. And at the last point, the recycling for circularity purposes. And all these activities were supported by IP management training, LCA and LCCA, standardization, regulation, monitoring, dissemination, and communication. So what are the objectives of Flamingo? As mentioned before, solid state mechanical alloying, the production of additives in this high energy power mill. We call it master batches with different compositions. Also, next, the casting of aluminium nano composites components by inoculating the additives or the master batch in an aluminium melt, and for homogeneous distribution of the nanoparticles, a combination of ultrasonic treatment was conducted, and steering as well, and different steering methods, let's say. The production of the components by low pressure die casting and greensand casting to demonstrate broader feasibility and applicability of the aluminium material. Also, the extrusion of cast billets for making profiles for the body frame. The weldability assessment using a range of welding technologies, the topology optimization and process simulation, and enabling the reduction of material per part without losing mechanical properties, and the usage of these components for substitution of steel and aluminum parts in electric vehicles. Validation of recycling supported also by the use of secondary aluminum. So here is the path, a diagram where we start with a primary and a secondary aluminum, go to the melting process, the foundry where we add the master batch and the nanoparticles, then to the production plant, the extrusion, the die casting in combination with topology optimization, and after that we test the components in the vehicle and to have a look on the recycling and safety issues, and also on the LCA, and then close the circularity and guarantee the environmental sustainability. And the nanoparticles will follow all these steps, starting from the melting process till the final product and the recycling, where we can use the nanoparticles in the secondary aluminum as well then. So here we see how the component changed from steel to aluminum by topology optimization and nanoparticle reinforced aluminum. We have a total different shape and geometry. This is not the final product yet. We did also some further improvements of that to make it more castable and easier to produce the sand models, and also for later on for the low pressure die casting for the steel molds. The following 5 phases are included during the project. In the first phase, the identification of the nanoparticles and alloy combinations were carried out to ensure best results. Then the development of dispersion and casting technologies, ultrasonic and different steering methods were used to ensure a homogeneous distribution. In the third phase, the topology optimization was performed with properties of nanoparticle reinforced aluminum by finite element methods. And in the fourth phase, the characterization by non-destructive testing and destructive testing. And the last part, recycling, to ensure circularity and environmental sustainability. So I would like to take the opportunity to briefly introduce the ÖGI, the Österreichische Designinstitute, or in English, let's say Austrian Foundry Research Institute, and how we implementing the knowledge gained in the project. We make about 60% of our turnover in the industry, especially in the automotive sector, and about 35 through research projects. Currently, we are involved in 20 projects, both national and European ones. Here we can see also our research and development areas. One of them is the technology transfer. All foundries in Austria are members of our institute, and we act as a training center for their employees. And in the future, knowledge about nanoparticles and the safe handling of them will be implemented in the training of these employees. So let's jump to the topic of health and safety and the safe handling with nanomaterials. The research and testing activities in Flamingo are not expected to cause direct harm to the environment. All the activities are conducted in controlled environments in which the relevant guidelines and legislations are applied. But to ensure this, the following points must be taken into account. The working area must be isolated. Also, a fume cabinet must fit it with filters. The workers have all full face masks, and also the additional training for handling with nanoparticles is important for all workers in the foundry. So, a method to prevent working with pure nanoparticles is to disperse nanoparticles through solid-state processing methods as mechanical alloying that allows production of homogeneous materials. Use a powder metallurgy approach. So MBN has the possibility to do this through high energy milling, producing master batches that we use further in the foundry with different compositions and amounts of nanoparticles. Here is you see we tried aluminium with 30% of nanosilicon carbides as nanoparticles, and also some combinations with zinc and copper, and also nanoparticles of titanium dioxide. The good thing is about after this production, you have a powder in the scale of about 100 to 200 micrometers, which is easy to work with. So, what are the impact of Flamingo, the short-term impact and the medium-term impact? So in short term, we can say you can gain more off-road capabilities because of the better components, the lighter weight, and the higher performing. You can enable more functions in utility vehicles. Also increase the working area of the fleet, and enable more flexibility in the configuration of the vehicle. On a medium-term impact, here we can say that establish guidelines for saving environment using materials with nanoparticles, also to establish guidelines for recycling in compliance with current aluminum recycling methods, to provide the automotive industry with wider portfolio of sustainable material, and also to support standard and regulation to include aluminum metal matrix nanocomposite, and manufacturing guidelines for better repeatability for casting and welding in particular. So I'm almost finished with my presentation, and I want to say there will not be a single solution for a lightweight electro vehicle. We need to put together results in a portfolio and pushing the same direction and sharing baselines and practices. So thank you for your attention.
Thank you. Thank you, Tose, for that presentation. That was very interesting. I see that there's also a lively chat also on questions, and please keep it up. And if you have any questions for Tose, also please make sure that you put them in there. My next presentation, or our next presentation, will be from Revolution. We have Ms. Andrea Martos from Edenet, who will be talking specifically about building skills for sustainable lightweight materials and digitization techniques development in the automotive industry. So, yeah, Andrea, can you please?
Thank you, Jose.
Take the floor.
Okay, I don't know if you can see my screen. I'm full screen now.
No.
Everything is okay?
Full. No, you're not sharing anything.
I'm not sharing?
No.
This works. A few minutes ago, I don't know what
It
happened. Okay. Again.
did.
Now, can you see my
Now,
screen?
yes, now we're seeing the
Okay.
screen.
And now in full screen?
Now you're in full screen. Perfect.
Okay, so thank you so much, Jose. I will present as my colleagues explain the Revolution project, mainly focusing on the digitalization techniques development across the automotive industry. I'm Andrea Martos. I'm from Eidener, the enterprise in charge of these activities in the Revolution project, and now I'm acting as part of the communication and dissemination team. So I hope to defend this part correctly for all of you. Well, as a general concept, Revolution proposed the lightweighting of the material in the car components in order to try to improve the autonomy of these electric vehicles. But concretely, in the digitalization, Revolution proposed a disruptive innovation in the injection molding, applying machine learning and artificial intelligence in order to optimize how the material, in this case recycled material, enter to the system and is formed in the process of the phone injection molding in order to improve the target of this piece and deliver high quality parts. We in Revolution are 14 partners from 10 countries, accounting more than 5 million euros budget, with a timing of 3 years of implementation framed in the HEY 2020 framework. And this is an innovation action, and we account 4 case studies to replicate and demonstrate the process in different parts of the vehicle that I explained a few minutes in some minutes. So we have partners really big in the automotive industry, as Far Plus and TOFAS and CRF, part of the Stellantis group in Europe. And we have research and technology organization as BTT, Norner, Eidener, and Fraunhofer, and enterprises dedicated to the material development as Trinseo, IMEC, Hetland, and LyondellBasell. So the overview of the project, as I said, this is we follow, or our intention is we will finalize the digitalization and control system of the automotive injection molding process step, and to construct and develop one platform, trying to improve the lightweight, the performance of the piece, and the end of life advantages at dismantling step. So this machine learning and artificial intelligence will optimize the recycled materials, because the idea is to try to improve the target or the quantity of recycled material we can use to be used in the automotive parts, and the injection molding process, trying to improve the efficiency of this step of manufacturing chain. This A platform will use the data from the 3 areas of production process to predict the quality when they will be used in the part, and all of this concept will be used for future electric vehicles, because, as you probably know, one of the main problems of the electric vehicles is the autonomy. And if we improve the lightweight and the cost by reducing the parts that are discarded frequently, we can improve the competitiveness of these electric vehicles. Regarding the digitalization, we have two main goals with this simulation and improvement. One of them is to reduce the weight of the components between the 10 and 40% compared to the current alternatives, and to demonstrate that at least 18% of the components of the selected use case can be recovered for recycling. The implementation of the project is based on four main pillars. One is the optimization of advanced light materials. This means experimental laboratory test in order to try to find materials that are more lightweight than the conventional ones. The second pillar of the implementation is the development of the advanced process control. This process control will be mainly focused on the part of the foam injection molding. So if we taking into account the previous pillar, the lightweight, so our idea is not only to reduce the weight of those pieces, but also to try to improve the target of how this piece can be recycled to the system again, and this can reduce the cost, the overall cost of the piece. The third pillar is the modeling and design. So we carefully model and design each piece and simulate how this will be, how will be the behavior of those parts in the cart and in the recycling steps. And the final, but not the last, but not the least part of the implementation is the demonstration of and validation of those pieces in real case study that I explain now. All this implementation, technical implementation, will be supported with the assessment in an environmental, social, and techno-economic point of view. We constructed from the beginning of the project an exploitation plan to perform and to try to exploit the results of the project in the best way, and with the communication and dissemination activities that will open us hopefully the opportunities, new opportunities to follow the work of Revolution, because we are on the last year of implementation. So hopefully we will have some opportunities to try to continue with the research in this way. The use cases. First one is the basic panel. This basic panel is in the boot of the car. It's a cover piece made frequently from with steel sheets and welded to a metallic frame. So our idea is that Revolution will build this component using one polymer, cell-reinforced polyolefin, saving the 55% of the overall weight. This case study is being demonstrated in CRF, that is part of the Stellantis group, and with very successful results. The B-pillar cover is this part from between the two doors of the car. This is in this case study particularly. The improvement is not only on the material side, because we will use post-industrially recycled PMMA to develop this piece. Is also in the part of the system on how we inject the material in the injection molding, because now it's manufactured in 2K dual part. It's a two-step process to have the final piece. And now we are testing and demonstrating that this could be passed to a monomaterial injection molded component only in one step, saving not only a cost but also time in the production of this component for the automobile. The car's crash box is a part that is this part that when you have a shock should be replaced because it's a safety component. So here the requirements and the parameters should be more exhaustive than in previous one, because this is a safety component. Now the crash boxes are produced by steel, and we propose to have 100% polymer solution, facilitating to recycle the components of this part of the vehicle in Tofaş. That is the enterprise demonstrating this part of the vehicle. And lower rear bumper demonstrated by Tofaş 2. This is an aesthetical part, colored frequently. That many times is really difficult to have the appropriate color and gloss using the recycled materials, and also keep the mechanical and physical properties of this part. So now we demonstrated that reducing 20% in the weight using PCR and PP, polypropylene, we keep the aspect and properties with the same quality than the conventional pieces. And now to finalize some environmental assessment highlights from the evaluation with the digitalization and control system and without. We identified that the principal or the main source for global warming are the raw material used. So using the approach of the control system and artificial intelligence, we impact directly in the 4-case study, because we propose to replace the conventional materials for recycled one, improving our the final environmental analysis. The transport of materials are relevant when the distance is higher. So improving, for example, in the case of the B pillar, to have one only step and not to pass to different enterprises and so on. We improve, of course, our target and our environmental view. And in the metal piece, in the conventional scenario, the welding is a really important source of impact due to the electricity and the production of fume welding. And by following this and by applying this control system, we remove the steel and the metal pieces, so we improve too the environmental aspects. And this is all from my side. Thank you so much for attending to this webinar. Here is my email and the email from the coordinator if you have a special interest to collaborate or to have joint development with the Revolution project. Thank you.
Thank you very much, Andrea, and we will now go on to the next project, which is levies, which will be presented by Clara Valero Lázaro, and Guan Gong will follow her after this. So please, if you can share your screen.
Yeah, thank you for the presentation. I'm trying to share my screen. Let me know when you can see the presentation remote.
It's fine. Perfect.
It's okay?
Yes.
Yeah, great. So yeah, I will present the LEVIS project together with my colleague Guan Gong from RISE in Sweden. My name is Clara Valero and I work at ITA Innova in Spain. So first of all, here it is a brief overview of the LEVIS project. It is a 3-year project, so we will be finishing next January. And we, ITA Innova, are the project coordinators, and the consortium is integrated by 13 partners. We are both research institutes and also industrial partners from 7 different countries. Okay, so as for all the projects, the main or one of the main objectives of LEVIS is to manufacture or to create lighter components for electric vehicles. In this case, we have chosen 4 demonstrators to apply our tools or our methods. Those are the suspension control arm, a battery box, a module box, and the stereo column carrier group of across car beam. And basically, the tools or methodologies that in which we focus on are the design and development of new materials, lighter materials, and materials with advanced properties. The design of manufacturing and assembly, new assembly technologies. We support these parts with the analysis of the structural integrity and life prediction of our components. That's a computational block. We are also introducing structural health monitoring systems in some of our demonstrators. We also focus on what happened with our components and materials when they are no longer useful. So we focus on end-of-life approaches, and obviously all of these parts or methodologies are analyzed with environmental or their environmental and techno-economic impact is well analyzed with different tools. The final objective is to be able to replicate what we learn with these 4 demonstrators in different electric vehicle components. So in this presentation, we are going to focus on those 2 aspects. I will first give you some ideas about the analysis of the structural integrity of the components, and then Guan will present some end-of-life approaches that we are developing at LEVIS. So the first tool or one of the tools that we use to create or to design lighter components are simulation methods for accurate failures or service life prediction, and also for design optimization. So the methodology that we propose in LEVIS follow this simulation workflow. It combines both process simulation or material characterization together with mechanical or structural analysis. So basically, we begin with some basic information about our components, such as the geometry or information about the material. We focus on multi-material solutions, so we combine, for example, metals and composites. So in those composites, we need information about the volumetric fraction of fibers that we use, their mechanical properties, and so on. We also have information about the manufacturing process. So we can perform these simulations and we obtain more detailed information of our component. For example, if we are going to have micro porosity, how the fibers are going to be reoriented during the manufacturing process, if we or if there are internal stresses or strains induced during the manufacturing. So with this information, we can create a more detailed model for the structural simulation, which at the end gives us the information that we want to know. I will show you here one example from the project, more focused on the analysis of the structural stability part. In this case, the demonstrator that we are designing is an internal beam from a battery box. And the solution that is proposed in LEVIS is a multi-material beam that combines an aluminum profile and a composite profile, both bonded by an adhesive. So, well, in general, we have to consider some aspects when we want to, before we begin our simulation campaign. So in general, we have to check, or we need to have an accurate definition of the geometry of our component. Also considering how this component is going to interact with other components in the whole assembly. We need to define properly the material based on different methods, both experimental or computational, if needed. We have also to define clearly which simulations we need to, or we want to do in order to confirm structural stability. And also we need to define the failure criteria for this material. So basically, we need to define what we know, what we want to know, and how we can know it. And that's what I'm going to show you in the next slides for this specific example. So, for example, as I've said, we need a proper material definition. So in LEVIS, we have worked both well, ideally, we would have the mechanical characterization of our materials based on different experimental tests. But when this is not possible, we can complement those experimental tests with computational methods that help us to have more detailed properties that cannot be estimated otherwise. And we can also introduce effects created or observed in the process simulations. For example, we have observed that in some cases the fibers reoriented, or that depending on the manufacturing conditions, there is going to be, for example, porosity and so on. So we can modify these conditions in order to have a better, let's say, component. So, for example, also in this case, we used micromechanics models to estimate some mechanical properties that were not possible to obtain experimentally. And well, we also obtain or we can estimate, for example, thermal properties that are not easily obtained in experimental tests, and so on. Then we need to define which well, I haven't said it before, but we basically use finite element models in LEVIS. So we need to define which simulations are the more suitable ones for our component. they can be focused on both mechanical or thermal loads, because the components that we are analyzing here are sometimes under high temperature changes. So it's also a very important aspect that must be checked. Also, we can, if we observe that we have some zone that might be critical, we can create more detailed models in order to check specifically in that zone how the component is going to behave. So we define all this simulation campaign, and then once that we have the let's say our results, we need to post-process them in order to obtain an estimation of the service life or the stability of our component. So in this case, we have defined different failure criteria for each material, taking into account the specific behavior of each material. For example, if we have isotropic or anisotropic materials, failure is defined on differently. So with this strategy, we can detect let's say the weakest link in our multi-material components. So we can focus on the weakest part, and we can propose modification of the materials, geometry, and so on. Because when one of the material fails, the whole component is considered to have failed also. So to summary this part, well, we combine process and structural simulations. We also combine experimental and computational information to create accurate models. And this strategy gives us the possibility of investigate easily different materials, geometries, conditions of the manufacturing process, and so on. So now I will give the floor to my colleague Juan.
Juan, you're on mute.
Sorry, I just remembered to turn on the camera. Thank you very much for the reminding, and thank you very much, Clara, for the very nice presentation. I will continue. Good morning, everyone. My name is Guan Gong, and I'm a senior researcher working at the RISE Research Institute of Sweden. Today, I will present some central progress in the work package in the LEVIS project, which is dedicated to the strategies and approaches for the end-of-life composite parts and materials that is being developed and recycled in the project. The work done in this task includes a thorough review on the state-of-the-art recycling technologies for both thermoset and thermoplastic carbon fiber composite since 1990s, which is then combined with market relevance and opportunities for recycled carbon fiber composite and related recycling processes, for instance, for the road vehicles. During the execution, a proposal of an overall end-of-life approach adequate for the range of materials, processes, and design solutions addressed in the LEVIS project was developed. And in all its scope, it is presented as a prospective possible strategy that could be implemented in parallel to the introduction of the technologies in the market. Appropriate recycling approaches were developed based on different thermoplastic polymers used in the LEVIS demonstrators. The work also involves validation through performing a life cycle analysis using the test result. So the first thing we have to say is what is the prerequisite for the closed-loop recyclable carbon fiber reinforced polymer and the relative closed-loop recycling process? Is that the composite waste, specifically the composite end of life in the LEVIS project, must be harvested with a maximum returned value, which can only be achieved by a systemic approach for sorting, inspection, characterization, and dismantling. Although the development of specific procedures in all those operations that I mentioned is out of the scope of this project, it is still considered that an end-of-life strategy proposal must take all these aspects into consideration. And furthermore, to enable the whole composite industry to be well positioned in the circular economy and advance the digital ecosystems, as shown in the picture, the left side, needs to be promptly developed. So in this digital platform or the ecosystem, materials market, design function, online and offline testing function, as well as the environmental impact evaluation must be implemented and also to generate and verify and demonstrate the most effective, environmentally beneficial and profit composite reuse and recycling strategies. And so until now, many sorting, non-destructive testing, inspection and dismantling techniques were or are being developed for separating multi-material composite structures. However, a critical step of evaluating the overall agent or service status of the composite part or the structures is usually missing. And here we must distinguish two concepts, the end of life of a material and the end of life of a part, application or product from each other. The end of life of a material is reached when no more value can be extracted from it. The end of life of a part, application or product is attained when it can no longer serve its original purpose. For instance, if a car reaches its maximum mileage. Both material and applications can have multiple lifetimes. For instance, an application or a product can reach its end of life, and the materials contained in it still possess potential for several more life cycles. Therefore, the evaluation of the overall agent and service status of the composite end-of-life parts indeed has the most significant influence on the reuse efficiency and the quality of the new composite product based on the end-of-life parts. So if the materials in the end-of-life parts are severely aged or degraded, reaching the material's end of life, then the whole composite end of life part will not be reliable for reuse in spite of very few or light defects or damaged zones are detected. And also, when we are trying to dismantle and shred the end of life parts prior to the new product design or development, this will also limit the reuse effectiveness. Therefore, in order to address this kind of challenge of understanding the overall agent and the service status of the end-of-life composite parts, a methodology as shown on the right side of this slide, this methodology capable of combining different tools, techniques, and sources of information in a smart way will be developed and to obtain a high quality and complete end-of-life composite part characterization with minimized effort. So virtual testing and micromechanical models will be combined with the machine learning and reduced order model technique, which together make up a prospective concept and the method designed for the end-of-life composite parts evaluation as specified in this sketch. Next slide, please. So the overall rule underpinning the end-of-life strategies, which is not limited only in EnlightEVs project, are firstly, the parts without damage would be directly used in manufacturing of new structures with identical or similar requirements. And correspondingly, the integration will be verified, so the reused part will not become defects in the newly manufactured structures. And secondly, parts with minor damages, which occur mostly in the resin-rich regions, would be repaired by, for instance, remelting or refilling with the recyclable matrix resin, and then used for new structures with comparable requirements. and correspondingly, the repairing efficiency and the characteristic properties of the repaired parts will be verified. And the third one is parts with catastrophic damages, which occurs mostly throughout the fiber reinforcement and that cannot be repaired, which instead will be used for recovering of fiber reinforcement resins and chemicals. And as Clara has mentioned, in the LEVIS project, we have 3 categories of carbon fiber reinforced thermoplastic demonstrators being developed. Demo 1 is suspension control arm. Demo 2A is a battering pack, which contains 3 sub-demonstrators, the upper cover, side beam, and internal profiles. Demo 2B and is the battery module housing, and demonstrate the cross carbon. So in total, there will be indeed 6 components to be studied regarding the end-of-life strategy. However, those components can be categorized by the thermoplastic matrix and by the design if they are neat carbon fiber reinforced thermoplastic composite, or they will be hybridized with metallic part. So based on this kind of classification, we can see that there were 2 types of thermoplastics matrix in the LEVIS project. One is the aliphatic polyamide, PA6 and PA66, and the other one is liquid thermoplastic alien resin, which includes the methyl metaacrylate. And some of them are neat composite, polymer composite, and some others are hybridized with either aluminum parts or steel parts. So next slide, please. So we can also briefly introduce the progress of the recycling of alien resin-based carbon fiber reinforced composite. So here we use a low temperature pyrolysis process in nitrogen atmosphere at 420 degrees for 4 hours. As you can see here, the carbon fiber fabric keeps a good structure integrity after the pyrolysis, which is beneficial for the cost manufacturing of the secondary composite. And the product out of the pyrolysis process are many recycled carbon fiber fabrics and the crude oil, and the gas amount is only around 3% of the whole. So, and the GCMS spectral analysis done with the crude oil shows a stole and a strong peak of MMA, which is the reactive monomer of the alien resin. So those results indicate that most materials in the carbon fiber reinforced thermoplastic that is recycled at this project is being preserved instead of decomposed into gas. And after comparison with the standard MMA, the purity and the content of MMA in the crude oil out of the pyrolysis process can also be calculated, and we can also collect the MMA from the crude oil. And then we also use the single fiber test for a couple of hundreds of fibers and to measure the strength and modulus of the recycled carbon fiber. And we found that 85% of the tensile strength of the carbon fiber is preserved and the modulus is almost not influenced. So that is all for my presentation for today. Thank you.
Thank you very much, Gwen, for that presentation, and also to Clara for the first section. We are running a little bit over time, but we do hopefully still have a little bit of time for some questions and perhaps some discussion. I would like to introduce, in any case, right now, Miriam Vendrell-Bosch from EURECAT, who will be moderating a quick question and answer session. I hope that most of you will be able to stay on for some of the questions and answer sessions. And if not, at least we would like to say thank you for attending. But please do stick around. It should be an interesting question and answer session. So please, Miriam.
Yes, I have seen that some of the questions on the chat have already answered, so to be as quick as possible, yes, I will take a look. Yes, we have a first question from Maurizio Maggiore. I don't know if it's here now, but yes, for ALMA speakers, I don't know, Vanessa or Pascal or Tom, if some of you can answer. Maurizio asked if isn't keeping the assembly project a strong limit in the potential for innovation? Wouldn't adding a no-limit approach also be needed to see how much potential there is in alternative technologies?
Yeah, I think that Maurice is referring to our consideration in the assembly line compatibility of our innovations. So in my view, it depends on if you are targeting short-term or long-term innovations. As you know, this project is an innovation action, so we deal with pretty high TRLs, something that can be applied in a relatively short term. So in this sense, since the assembly line is something well, quite expensive to change and it's very time demanding, we focused on innovations that are mostly compatible with the existing ones in order to introduce them in the short term, something like 2 years, 3 years after the end of the project. So this is the main reason, but of course it's limiting. Yeah, we can do something much more disruptive if we think in the long term, but it's not under the scope of pharma project.
Okay, thank you, Vanessa. Now we have also a question for Violeta from EURECAT of Fatigue for Light project, and regarding the methodology that you presented before, can this methodology be applied to other sectors or cases aside than mobility?
Yes, of course. We were aiming for this general methodology that you can apply to any kind of study, but it requires a very, like, a consortium or a group of designers that are very committed to this work. But it could be applied to any case. Yeah.
Okay, thanks, Violeta. Now I'm checking on the chat. Yes, from Tose from Flamingo project. How do you see the potential for a large-scale technological implementation, and is it economically sustainable?
Yes, hello. Thank you for the question. From our point of view, we did our trials and our casting in a 40-kilogram crucible, and we need some kind of ultrasonic treatment to break up these clusters from the master batch and to distribute the nanoparticles homogeneously. I will switch on my camera. So this amount, it works fine, but if you imagine to do that on a large crucible of 500 kilograms, the unit is just too small, and there is more research needed. But of course, if you can implement it in a larger scale, it would also be sustainability and good working. So, but I think this could be also another project or a further project for that.
Okay, great. Thank you so much.
Thank you.
Now I see a question from Christian Leroy to Andrea Dominguez. He asked if you can clarify, Andrea, the end-of-life advantages that you will develop with the project.
Yeah, I was answering him by the chat, but in any case, the aim of this or the improvement in the end of life is that those parts that we are converting to polymer solution are can be dismantling better than the steel ones, and improve the capability to crush those pieces and to introduce again in the loop of the process.
Okay, and we have another question for you, Andrea, regarding the first results on sustainability reports. Which are the main steps to reduce the emissions in the car manufacturing, ensuring the lightweight of the materials?
Sorry, I didn't see this. From Pascal.
No, it's not from Pascal, this one.
Okay, can you repeat, please?
Yes, regarding the first results on sustainability reports, which are the main steps to reduce the emissions in the car manufacturing, ensuring the lightweight of the materials?
Okay, yeah, the main is to replace all the pieces that we can, that are made from steel or metal pieces into polymer solutions, because the steel and metal pieces are high, are difficult to recycle and so on. And the second one, I think that I explained at the end, is to try to simplify the process for manufacturing, trying to do some process that are now 2, 3, or 4 steps in single steps. And this reduce the electricity and improve the the environmental analysis.
Okay, thank you, Andrea. I see another question from Christian Leroy to Guan Gong from Levy's project. Did you analyze the main challenges to implement your proposed solutions considering the current ELV treatment practices?
Yeah, I was planning to write on chat, but then I said maybe I can directly talk. Yes, we have analyzed, and to be honest, that's why I said for this specific project, what we did is a thorough check of the literature study and combined with expertise and experience from different partners who has been intensively working on the composite recycle and reuse. Due to that, we have a limited budget and time scale, so we cannot actually really carry out the practical work. Instead, we combined our knowledge and know-how to come up with, let's say, a general perspective and concept that we think that should be the future for the to promote or to boost the reuse and recycling on the composite. And specifically, we have some challenges. For instance, if it's a hybridized material, that the polymer composite is bonded to a metallic parts, we have developed by Itainova the controlled heating for dismantling in order to reduce the additional defects that could be introduced by the dismantling process. And then we also have LCA, and there is another challenge. We have figured out how to connect the end of life and the LCA, because we have to maybe develop a new module that can include the end of life into the LCA, so LCA not stopped. So that is I think this is a very good question, and we do have a lot of challenges. So I would be really happy to discuss with you after the meeting. Thank you.
Thank you. So yes, now continuing with the Levy's project speakers, maybe Clara Valero, we have a question. In your presentation, you have mentioned that you simulate manufacturing processes of components. Can you give us some examples of how this simulation can help in lightweighting?
Yeah, well, this process simulation is part of the workflow proposed, including simulation activities. So basically, it helps us to know if the manufacturing conditions that we are going to apply or that we are going to use are the proper ones. So, for example, we can test different ply orientations when we are manufacturing a composite component. We can check how the resin is injected, the temperature, the pressure. So the combination of these different variables can help us to decide if we can manufacture, for example, a thinner component with that fulfills the properties that we need. So it's part of the whole workflow.
Okay, maybe we can have time for two more questions. For Violeta from Fatigue for Life, how much of the environmental impact can be reduced with eco-design and LCA combo?
Okay. There is an estimation, like that is in general. If you apply eco-design from the beginning of the development of any kind of material or solution, or I'm not talking about electric vehicles or vehicles at all, it's just in general, it says that it's an 80% defined in the design at the beginning of the product. So if you eco-design at the beginning, you have all that range of improvement if you start at the beginning, and then it goes lowering along the life cycle of the product. If it's already been developed, then you can improve some parts, but not all of them. And then for usage and all, it's reducing over the time. But if you start at the beginning, it's an 80% of environmental impact from design.
Okay, thank you so much, Violeta. I see that we have a last question in the chat from Francesc Perarnau to Andrea Dominguez. He asked which kind of machine learning and platform do you use or are you developing?
Yeah, mainly the platform that we are using is, I cannot detail as much as all the information from the project is now confidential, but the process, the idea is to put some sensors and other kind of measurement equipment, and with this control system and machine learning, we are training this machine in order to only select the pieces that are okay, that has the enough quality to pass to the second stage, and the pieces that are not okay are recirculated to the process to reuse the pieces, trying to mile in again and so on. This is more or less the...
Okay, so yes, just a last question that we received just now from the chat for you also, Andrea. You are probably aiming at recycling at a part or alloy specific recycling. Is that the case?
Yes, this is the case. I'm so sorry, but because I have the feeling that I'm not explaining as well as my colleagues, my technical colleagues can. But in any case, if you still have question, you can contact me, because I put it my email and the email from the coordinator on the chat.
Yes, sure. Thank you, Andrea. I think that's all. Thank you all for the questions and for the interaction in the chat. I think it was really great to see all your comments during the presentation and the webinar. And Jose, correct me if I'm wrong, but maybe we can share with you the video in some days, and also presentations, and also the contact. So if you have any other question or you want to continue with some kind of discussion, sure, from our side and from the speaker side, we will be happy to talk with you and to continue with the discussion. So thank you all, and Jose for closing part.
Thank you very much, Miriam. Indeed, I would like to echo what you just said, that we will, of course, be sharing the video and materials from this webinar for everybody to also reference afterwards. We would also first like to apologize for running a little bit over time, and thank you all for the patience, for sticking with us until the end. I'm sure that the questions and answers were particularly useful to clarify the situation for the different projects and your interests. I would like to thank all of our presenters. We had 5 projects here today, all part of the EnlightEVs Cluster, working towards enlightening of our future EV vehicles. We thank them also for their efforts and for being here today to share with us their research and their progress. I would also like to thank, of course, the European Commission for recognizing us as an official Green Week event. We are definitely grateful for the opportunity to share what it is that we're doing with our projects, and in particular, of course, on how our projects can impact industry by making sure that all of the industry is aware and has the knowledge that they can also implement into their own designs and their own processes. Because in the end, I think Maurizio also put a little bit of an emphasis on what it is that should be the balance between what we try to aim for as innovation potential within our projects, but of course we also have to make them implementable and something that can be practically used in industry afterwards, which also means that we have to prepare what it is that we have, not only just for industry, but also make sure that we can transfer that knowledge effectively and efficiently to the people that have to use it. So that is what this EU Green Week is all about. So I would encourage you to look for other events and things that you can participate in and be part of during this week to make sure that you are also up to date on how you can play a part in this. And finally, of course, I would like to say thank you all of the attendees for joining us. We will, as previously mentioned, put everything online for your further reference afterwards. And I wish you all a great week ahead. Thank you very much.
Goodbye.
Thank you very much.
Thank you very much. Bye bye.
Thank you very
Have a
much.
good day.
Bye.